Draw an FBD of a puck sliding on frictionless ice. So let me start out by actually drawing what I think is maybe a picture of that situation. So let's imagine that this line represents some ice, and here is like maybe a hockey puck or something like that. I don't know if I'm very good at drawing hockey pucks, although it seems like a simple enough kind of thing, right? But I don't know, maybe I'll shade it in here or something. I don't know if that looks good or not. But there's that hockey puck, and it's sliding along in this frictionless ice. Well, if it's frictionless, Galileo has taught us that this thing will move in an inertial way. In other words, it'll maintain a constant velocity. So maybe I'll just have here a velocity vector describing that. And one of the rules that we've established is you don't put velocity vectors in an FBD, but it's perfectly okay to put that in this picture to indicate that it is, in fact, sliding. So now I'm going to go to the FBD. It is actually optional if you want to put this label FBD. You don't necessarily have to do it. I'm doing it for clarity's sake. But if somebody just drew a point and then started drawing forces, like I'd probably be able to figure out, okay, they're doing an FBD. What's a good starting point for this? I think a really good starting point pretty much always if you're doing something on Earth is to say, hey, there's going to be a force of gravity. And in this class, I'm going to commonly label that with an F sub G. Although there are other options. You can use a word. I think that the answer in this slide will use the word gravity as it did before. I think it makes sense that the ice is probably supporting this puck, and so I think there's going to be a normal force. So, okay, are we done? Is that all the forces that we need? I mean, it's sliding. Surely there must be some force pointing in the direction of that slide, right? That's what Aristotle thought. So I'm mentioning that because that's been one of the most common pitfalls I've seen in this class, is that somebody will be looking at a problem like this or similar to this, and we just have this like human intuitive need to somehow explain how this is happening, how this object is moving, and a lot of times the response to that will be to try to put in some force to explain it. But you actually don't need it. All you need is the explanation that there is no friction. In that sense, had there been friction, I think there would have been some kind of horizontal force, maybe pointing in the opposite direction of this velocity to represent that friction. But in the absence of friction, there is no force. These forces balance out. Net force is equal to 0. Newton's first law is being obeyed because this thing is just continuing to slide over the ice, as Galileo knew that it would. So let's look at the answer here, because I've got it in pictures here, maybe better than I just did on my whiteboard. So there's a puck on ice. Oh, I guess it's moving the opposite direction that I drew it. That's okay. In fact, will that even affect the FBD based on what we just did? I don't think so, right? So there's the system point. There's a downward force, presumably for gravity. There's a label. There's gravity. There's an upward normal force, and we're saying it could be called the support or the normal force. And again, those forces are really all that's necessary to explain what's going on here. We don't need to add more forces to explain a velocity.